On August 15, 1940, the most important movement in Britain's air defense was not a fighter taking off. It was a thin spike lifting from a green line. At a chain home station on the south coast, an operator leaned toward a cathode ray tube, measured the echo, and passed a range and bearing into a telephone. Miles away, a wooden block began moving across a map. Then a sector controller reached for another phone, and fighters began to climb. The Luftwaffe had more aircraft. Britain had built something Germany did not have over the channel, a nervous system. By the summer of 1940, France had fallen. German airfields now crowded the coast from Normandy to the Low Countries, close enough for bombers and fighters to cross the channel in minutes. The invasion plan called for the Royal Air Force to be beaten first. Fighter Command could not answer by keeping every Hurricane and Spitfire in the sky. Continuous patrols would burn fuel, exhaust pilots, and wear out engines before the enemy even appeared. Britain's problem was not simply how to see the Luftwaffe. It was how to know where the raid was going, decide which squadrons to use, and put them at the correct height before the bombers arrived. That problem had been waiting for a solution since February 1935. Near Daventry, physicist Robert Watson Watt and his assistant Arnold Wilkins arranged a crude experiment using signals from a BBC transmitter. A Handley Page Hayford bomber crossed the area, and the receiver caught the radio energy reflected from the aircraft. The return was weak. The idea behind it was enormous. Within 4 years, 21 operational chain home stations guarded Britain's exposed coast. Their steel transmitting towers rose roughly 360 feet above fields and cliffs. The equipment could detect high-flying formations at long range, sometimes while they were still assembling over France. But early radar was not a magic eye. It did not draw a clean picture of the sky. It produced pulses, estimates, uncertainty, and duplicate reports. It struggled with aircraft flying low. Once a raid crossed inland, the radar picture weakened and the Royal Observer Corps had to continue the track by sight and sound. A warning that stayed inside a radar hut was useless. Hugh Dowding understood that before the war began. As commander of Fighter Command, he helped build an organization around the technology. Radar stations, observer posts, telephone lines, filter rooms, group headquarters, sector controls, airfields, radios, anti-aircraft batteries, and maintenance crews. Today it is called the Dowding system. In 1940, many of the people inside it simply called it the system. Reports from several radar stations arrived at Fighter Command headquarters at Bentley Priory. Because neighboring stations could see the same formation, the information had to be compared and filtered into one usable track. RAF plotters worked around a large map table, moving counters with long wooden rakes. Telephone operators repeated bearings, strengths, heights, and directions. Officers watched the colored markers in the sector clock, deciding which reports belonged to the same raid and which might be false. The cleaned picture then moved to the group headquarters responsible for the threatened region. For Southeast England and London, that meant Number 11 Group at Uxbridge, commanded by Air Vice Marshal Keith Park. There, another map showed the raid approaching, the location of friendly squadrons, the condition of sector airfields, and which units were ready, refueling, climbing, fighting, or returning. Park did not need to launch everything. He needed to launch enough. That distinction saved aircraft, fuel, and men. From Uxbridge, orders moved to sector stations such as Biggin Hill, Kenley, Hornchurch, North Weald, and Tangmere. Controllers there spoke directly to squadrons by radio, guiding them toward an interception. At the airfields, pilots waited beside their machines. Some sat in deck chairs. Some played cards. Some tried to sleep with boots on. When the telephone rang, the waiting ended. Ground crews pulled away chocks. Merlin engines coughed, caught, and hardened into a roar. Hurricanes and Spitfires rolled, lifted, and climbed toward a position chosen before most pilots had seen a single enemy aircraft. That was the hidden advantage. Radar did not make a British fighter faster. It made the fighter's time more valuable. A squadron that took off too early wasted fuel circling empty sky. A squadron that took off too late met bombs falling on its own runway. The system tried to place each unit inside the narrow strip of time between those two failures. And in August 1940, that strip became brutally thin. On August 12, German aircraft attacked several radar stations along the south coast. Buildings, power supplies, and communications were damaged. Ventnor on the Isle of Wight was knocked out for longer than the other sites. For a moment, the nervous system had open wounds, but the towers were difficult to destroy. Repair crews restored several stations quickly. Neighboring coverage and emergency procedures reduced the gaps. Most importantly, the Luftwaffe did not keep striking the network with the concentration needed to break it. The visible towers looked like the target. The real target was the flow of information. Germany never attacked that flow consistently enough. Then came August 18. The day would later be remembered as one of the hardest of the battle. At RAF Kenley, low-flying Dornier bombers approached beneath the most reliable coverage of the high-looking chain home sets. The raid hit the airfield hard. Hangars and buildings were wrecked. 10 aircraft were destroyed on the ground. The sector operations room had to move to an emergency location. For the men and women inside Fighter Command, the danger was suddenly obvious. The system was powerful, but it was not invulnerable. Its cables could be cut, its control rooms could be buried, its airfields could be cratered, and its pilots could not be manufactured. Britain was replacing fighters at an impressive rate, but experienced aircrew were disappearing faster than training could create equal replacements. A machine could leave a factory and join a squadron. A dead pilot could not. Every bad interception now cost more than metal. It cost the one resource Dowding could not rapidly rebuild. This was the darkest truth of the battle. Britain did not need to lose every fighter to be defeated. It only needed its defensive rhythm broken. A few radar gaps, a few severed telephone lines, a few sector stations knocked out at the same time. A few more exhausted squadrons sent to the wrong place. The Luftwaffe's numerical advantage would do the rest, but the system bent instead of breaking. Technicians patched cables under threat of renewed attack. Plotters continued working through dense waves of reports. Controllers shifted aircraft between damaged fields. Ground crews refueled and rearmed fighters in the open. The Royals Observer Corps picked up raids that radar lost over land or at low level. No single part was perfect. Together the parts kept producing decisions. That was the real mechanism behind Britain's defense. Not radar alone, not the Spitfire alone. Not one commander, one pilot, or one heroic afternoon. The advantage came from connecting imperfect information to a usable decision faster than the enemy could exploit it. The difference could be measured in minutes. Those minutes allowed pilots to remain on the ground until a raid was real. They allowed controllers to choose a likely interception point. They allowed fighters to climb toward altitude instead of chasing bombers from below. And they forced German escorts to spend their most limited resource: fuel. The Messerschmitt Bf 109 was a dangerous fighter, but its range over southern England was restricted. The longer a formation remained in British airspace, the closer its escorts came to the moment they had to turn for France. British controllers understood the geography. They did not need to destroy every attacker. They needed to make the raid late, scattered, nervous, and expensive. By early September, pressure on Fighter Command's southern airfields was severe. Then on September 7, the main German effort shifted toward London. The capital suffered terribly, but the change also gave battered sector stations a measure of relief. Runways were repaired. Communications were restored. Squadrons were rotated. The network recovered enough strength to keep meeting the daylight raids. The Luftwaffe believed Fighter Command was close to collapse. The plots on British map tables showed something else. On September 15, large German formations crossed the Channel in 2 major waves. Chain home stations detected them. The information moved through Bentley Priory, into number 11 Group, and outward to the sectors. Keith Park could see the size and direction of the attack developing before the bombers reached London. He committed his squadrons carefully, then called for reinforcement. Across southern England, fighters climbed into a sky already filling with contrails. The air battle was violent and confused. Pilots saw only fragments: a bomber sliding beneath a wing, tracer passing a canopy, an escort diving out of the sun, smoke bending toward the Thames. But below them, the system held the larger picture. The raids were broken up. 2 days later, Hitler postponed the invasion preparations known as Operation Sea Lion. The daylight offensive continued, but the possibility of destroying Fighter Command quickly had passed. The Battle of Britain is remembered through aircraft: the elliptical wings of the Spitfire, the heavier silhouette of the Hurricane, the dark formations crossing the Channel. But the decisive picture was often less dramatic. A headset pressed against one ear, a technician replacing a burned cable, a telephone operator repeating a bearing, a DOAF plotter pushing a wooden block across a map, a controller waiting 3 more seconds before giving the order to scramble. Thousands of small actions turned a crude radar echo into concentrated air power. That was why a smaller fighter force could meet a larger attacker without wasting itself in permanent patrols. That was why damaged stations could keep contributing. That was why the Luftwaffe repeatedly found British squadrons waiting near the right place instead of searching an empty sky. Britain did not win because its machines saw everything they did not. It survived because the warning moved, from tower to telephone to map to decision to cockpit, before the enemy arrived. The radar pulse never fired a shot. It bought the minutes in which everyone else could.